A copper chaperone is a protein which binds intracellular copper and delivers it safely to essential intracellular locations. The primary function of a copper chaperone protein is to prevent unwanted and dangerous oxidizing reactions of copper as it travels through the cytoplasm. Unwanted redox cycling of copper causes a chain of aberrant chemical reactions that occur in the cell when unregulated copper-1 interacts with oxidative species and produces copper-2 and reactive oxygen species, or ROS. The reactive oxygen species, such as hydroxide radical, are hazardous to the health of the cell because of the potential impact of oxidative stress when they interact with surrounding proteins and surfaces, overall leading to the aging and potential death of the cell. This reaction is continually harmful because the copper-2 may be reduced to copper-1 and the cycle continues to cause cell damage as long as the metal remains free. If copper chaperones do not properly transport and protect intracellular copper, the reactive products of redox cycling will irreversibly damage the cell. In order to resolve the concern of redox cycling, the copper chaperone stabilizes one oxidative state of copper. The copper-1 oxidation state is selected to be stabilized because the cell is a reducing environment and prefers this state already. This study concentrates on the representative copper chaperone antioxidant 1, or ATX1 in shorthand. ATX1 is present in prokaryotes, but is studied with the application for human cells through the analogous protein ATOX1. Similarly, the CCC2 protein is analogous to the human protein ATPase 7A and B. The analog names are written in parentheses beside their prokaryote representative. ATX1 is a part of a chain of copper activity through the cell. This chain of activity includes copper transported through the cell membrane by CTR1 to ATX1 to the CCC2 protein and onward. In short, the ATX1 is a piece of a chain of copper transport, protection, and usage through the cell. ATX1 and all copper chaperones are integral features of copper transport within the cell, most importantly, stabilizing the copper-1 oxidation state in order to prevent the harm caused by redox cycling. The ionic size of each copper ion is compared here side by side. Copper-1 has a larger ionic radius than copper-2. According to the hard-soft acid-base theory, the radius and charge affects the softness of a metal such that copper-1, with its larger ionic radius, is a soft acid, and copper-2, which has a smaller ionic radius, is defined as borderline. The binding site of ATX1 is characterized by two cysteine residues, which contain a terminal sulfur when deprotonated. Also due to the atom's radius and large charge, sulfur is considered a soft base. The hard-soft acid-base theory follows the convention that soft bases prefer to bind with similarly soft acids. Thus, it is preferred that soft copper-1 binds with the soft sulfurs. The softness of the protein's binding site contributes to the selectivity of copper-1 over copper-2, because the borderline acid would not be selected when competing with the soft acid. Another critical difference between the copper-1 and copper-2 ions are the electron count and the effects of ligand field stabilization energy. Ligand field stabilization energy is another principle of coordination chemistry that can be applied to explain how ATX1 stabilizes the copper-1 oxidation state. Copper-1 is a D10 metal, meaning that there is a complete set of 10 electrons in its D shell and has an associated ligand field stabilization energy of 0. This ligand field stabilization energy of 0 means that copper 1 has no energy preference for one binding geometry over another. Thus, copper 1 will bind linearly to the chaperone when copper 2, which is a D9 metal with a non-zero ligand field stabilization energy, will not. The zero ligand field stabilization energy of copper 1 also assists in the transfer mechanism from the copper chaperone to another protein, such as CCC2. During the docking and transfer process to CCC2, copper forms an additional bond with an adjacent cysteine residue of the CCC2 protein before breaking any initial bonds with ATIX1. This capacity is also enabled by the electron count, with 10 electrons from the metal and 2 from each sulfur, which has not yet reached its capacity of 18. Thus, the geometry is able to transition from linear to trigonal-planar before breaking the bonds with ATIX1 and returning to a linear geometry at the CCC2 site. The 2-coordinate linear and 3-coordinate trigonal-planar complexes are both favorable to the copper 1 over the copper 2 due to the ligand field stabilization energy preference. This mechanism again promotes stability of copper 1 while disfavoring copper 2. Finally, the lability of the copper 1 reduces the energy cost of transport from ATIX1 to CCC2. When a metal ion is labile, this means that it reacts at a high kinetic rate and may readily replace ligands in coordination complexes. Copper, both as copper 2 and as copper 1, is especially labile. This lability comes as a result of the presence of electrons in the E sub g high-energy anti-bonding orbital. When these electrons are present in this higher energy state, they are more readily reactive, and thus are able to react faster as well. When the copper 1 enters the cell through CTR1, the copper chaperone complex binds and transports the copper through the cell to the metal's next binding site. The copper's high lability is utilized because the metal is able to change ligands readily. Thus, it can change from one transporter complex to another without high energy costs. The high lability of copper also gives further motivation to prevention of free copper in the cell, since it will also react rapidly with metabolism products to form reactive oxygen species. If the copper chaperone is successful in its cellular role, the selection and stabilization of one oxidative state of copper, specifically the copper 1 oxidation state, will reduce instances of oxidative stress and maintain the health of the cell at very low energy costs.